Hello there and welcome to the Sleepy Science Place. I'm so glad you found your way here tonight. Maybe you've had one of those days where the world felt a little too loud, a little too bright, a little too fast. Or maybe you're simply the kind of person who finds peace in looking upward, in letting your thoughts drift beyond the everyday and into the velvet darkness above. Either way, you're exactly where you need to be. Tonight we're going to explore something truly magical. The night sky, that endless canvas of stars and silence that has watched over humanity since the very beginning. We're going to wander together through facts that feel less like information and more like lullabies, gentle truths whispered by the cosmos itself. Before we begin our journey, if you're enjoying this content, I'd love it if you could subscribe to the channel and leave a like. It helps others find their way to this peaceful corner of the internet, and it lets me know that these quiet moments matter to you too. But there's no pressure. Just settle in, let your breathing slow, and know that for the next little while, your only job is to listen, to drift, and to let the wonders of the night sky carry you softly toward sleep. The night sky is perhaps the oldest story we know. Long before books, before language as we know it, before cities lit up the darkness with artificial glow, there was the sky. Our ancestors looked up at the same stars you can see tonight, though they saw them with different eyes, wove them into different stories. They used the sky as their calendar, their compass, their connection to something larger than themselves. And in a way, when we look up, we're continuing that ancient conversation, that timeless tradition of wonder. Tonight, we're not going to rush. There's no urgency here, no deadlines, no demands. We're simply going to let fact after fact wash over you like gentle waves, each one a small gift from the universe, each one an invitation to let go a little more. So find your most comfortable position, whether that's curled on your side, stretched out on your back, or nestled however feels right. Let your pillow hold the weight of your head. Let the blankets become clouds. And let's begin this soft exploration of the sky that waits above us all, patient and eternal, ready to receive our wonder and our weariness alike. When you look up at the night sky, you're looking backward through time. Light, for all its speed, still takes time to travel. And the stars are so impossibly far away that their light spends years, sometimes centuries or even millennia, crossing the darkness to reach your eyes. That star you're gazing at might not even exist anymore. It could have flickered out generations ago, but its light continues its faithful journey to you. In a very real sense, the night sky is a time machine, showing us not the universe as it is, but as it was. And there's something deeply comforting about that, isn't there? About knowing that when we look upward, we're seeing history written in light, stories that began long before we were born and will continue long after we're gone. The sky reminds us that we're part of something continuous, something that flows through time like a river flows through landscapes, patient and persistent and eternal. The darkness between the stars isn't empty at all. In fact, space is filled with something called the interstellar medium, vast clouds of gas and dust, hydrogen and helium mostly, drifting through the cosmic dark like fog through an ancient forest. These clouds are the nurseries of stars, the places where gravity slowly, patiently pulls matter together until it becomes dense enough, hot enough to ignite into new suns. Even in the apparent emptiness, creation is happening, slow and quiet and magnificent. When you close your eyes tonight and see darkness, imagine it not as absence but as potential, as the canvas upon which new light will eventually paint itself. The darkness is not the enemy of light. It's the space that holds it, the velvet backdrop that makes each star visible. Without the darkness, there would be no sky to wonder at, no stars to wish upon, no night to bring us this particular kind of peace. The moon, our faithful companion, is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. It's such a small distance, barely more than an inch, but given enough time, millions and millions of years, our moon will be noticeably farther than it is today. Ancient creatures that lived hundreds of millions of years ago saw a moon that loomed larger in the sky, closer and more imposing, and the days were shorter then too because the moon's gravity affects Earth's rotation. But for now, for your lifetime and mine, for all the nights we'll ever experience, the moon will be right where it's always been, rising and setting in its patient rhythm, waxing and waning like a cosmic breath. There's something soothing about knowing that even as it slowly journeys away, it does so at a pace so gentle that it's essentially changeless within the span of human experience. The moon will light your nights just as it lit your grandmother's nights, and her grandmothers before her. On a perfectly dark night, far from city lights, the human eye can see about 5,000 individual stars. But the Milky Way, our home galaxy, contains somewhere between 100 and 400 billion stars. That means that even on the darkest, clearest night imaginable, we're seeing only the tiniest fraction of our stellar neighborhood, like standing in a vast forest and being able to see only the few dozen trees closest to you while thousands more remain hidden in the darkness. And beyond our own galaxy, there are billions more galaxies, each containing billions of stars scattered through space like islands in an infinite ocean. The scale is so immense that it stops meaning anything in conventional terms. The numbers become poetry instead of mathematics, a way of saying more than you can imagine rather than a quantity you could actually count. But here's the beautiful thing. You don't need to see all the stars to feel their presence. Those few thousand visible points of light are ambassadors from the vastness, representatives of the cosmic multitude, and they're enough. They're more than enough. The North Star, Polaris, has guided travelers for centuries because of its seemingly fixed position in the sky. While other stars wheel around the celestial dome as Earth rotates, Polaris stays put, hovering above the North Pole like a faithful marker, a cosmic compass point that never wavers. But here's the gentle secret. Polaris wasn't always the North Star, and it won't be forever. Earth wobbles slightly on its axis over a cycle lasting about 26,000 years, and this wobble means that different stars take turns being the North Star. In ancient Egypt, thousands of years ago, a star called Thuban held that honor. Thousands of years from now, it will be a star called Vega's turn. But right now, in this moment, in this era of human history, Polaris is our anchor point. And maybe there's something reassuring about that too. About knowing that even our constants are temporary, that the universe is slowly dancing through changes so gradual they appear as stillness to us. Nothing is truly fixed, yet everything feels stable enough within the span of a human life. We live in the pause between long transformations, and that pause is spacious enough to feel like permanence. Shooting stars aren't stars at all, of course. They're meteors, tiny pieces of space debris, often no larger than a grain of sand, that burn up as they enter Earth's atmosphere at tremendous speeds. The friction with air molecules heats them to incandescence, and for just a moment, they streak across the sky, bright and brief and beautiful. Most of them are fragments left behind by comets, ancient icy visitors that shed dust as they swing through the inner solar system on their long, elliptical journeys around the sun. When Earth's orbit carries us through one of these debris trails, we get a meteor shower, dozens or even hundreds of shooting stars in a single night, all radiating from the same point in the sky like fireworks in slow motion. People have been wishing on shooting stars for centuries, a tradition that turns cosmic debris into vessels for hope, that transforms random physics into something magical and personal. And who's to say those wishes don't matter? Maybe what we're really doing is taking a moment to acknowledge something beautiful, to pause in gratitude and wonder, to connect a private hope to the vastness above us. Maybe the magic isn't in the meteor granting anything, but in us taking the time to wish at all. The stars you see are all part of our local neighborhood within the Milky Way. Even the faintest stars visible to the naked eye are, cosmically speaking, right next door. The farthest individual star most people can see without a telescope is around 16,000 light-years away, a number that sounds enormous, and it is, but it's a tiny fraction of our galaxy's 100,000 light-year diameter. We're seeing just our immediate stellar vicinity, the cosmic equivalent of looking out your window and seeing the houses on your block while an entire vast city sprawls beyond your view. And yet, those few thousand stars we can perceive have been enough to inspire every culture that has ever existed. Humans have found patterns in them, connected them into constellations, told stories about heroes and animals and gods all traced in light across the dark. The same small window into the galaxy has given rise to countless mythologies, navigational systems, calendars, and poems. We don't need to see everything to be moved by what we can see. Sometimes a limited view is exactly enough, exactly what we need to feel connected to something greater without being overwhelmed by its totality. The planets you can sometimes spot in the night sky don't twinkle the way stars do. This is because planets are close enough that they appear as tiny disks rather than single points of light. When you see a steady, bright point of light that doesn't flicker, you're probably looking at Venus, Jupiter, Mars, or Saturn. They follow a path across the sky called the ecliptic, the same path the sun and moon take, because we're all orbiting the same star in roughly the same plane. Ancient astronomers noticed these wandering stars and gave them special significance. The word planet comes from the Greek word for wanderer. There's something companionable about the planets, isn't there? There are siblings in the solar system, fellow travelers around the sun, close enough that we've visited some of them with our spacecraft, close enough that they feel less like distant mysteries and more like neighbors we're slowly getting to know. When you spot that bright point of light low on the horizon at dawn or dusk, steady and strong, that's often Venus, Earth's sister world, shining through a thick atmosphere of clouds, greeting you across the empty space between our two worlds. The Milky Way gets its name from ancient Greek mythology, from a story about the goddess Hera nursing the infant Hercules. When he pulled away, milk sprayed across the sky, creating the pale band of light we see arching overhead on dark nights. But nearly every culture has its own name and story for this luminous road across the heavens. In China, it was called the Silver River. In Finland, the Pathway of the Birds. In some Native American traditions, the Road of Souls. The scientific reality is just as poetic. What we're seeing is our galaxy viewed from inside, looking edge-on through the disk of stars that spiral around the galactic center. We're nestled in one of those spiral arms, gazing through the thickness of the galaxy itself, seeing the combined light of billions of stars too far away to distinguish individually, all blending into that soft, milky glow. It's like standing inside a vast meadow of luminous flowers and seeing them blur together into a field of light. We're not observing the galaxy from outside. We're part of it, embedded in it, seeing it from the most intimate perspective possible from within its very structure. Starlight is ancient by the time it reaches your eyes, but that's not the only way in which stars connect us to the past. The atoms in your body, the calcium in your bones, the iron in your blood, the oxygen you're breathing right now, were forged inside stars that died long before our solar system even existed. Stars are fusion furnaces, crushing hydrogen into helium, helium into carbon, and working their way up the periodic table through increasingly complex elements. When massive stars reach the end of their lives, they explode as supernovae, scattering those elements across space, seeding the cosmos with the raw materials for planets and life. The cloud of gas and dust that eventually collapsed to form our sun and Earth was enriched by these ancient stellar deaths. You are quite literally made of stardust. It's not a metaphor or poetic exaggeration, it's chemistry and physics. Every atom in your body except hydrogen was manufactured inside a star. You're the universe experiencing itself, cosmic matter that has become conscious enough to look back at the sky and wonder about its origins. How extraordinary is that? How perfectly, impossibly strange and beautiful. The darkness of space is one of the purest forms of silence we know. There's no air in space, no medium for sound waves to travel through, which means the cosmic realm is utterly, completely silent. All those explosions and collisions and stellar winds happen in perfect soundlessness. Even the most violent supernova, an explosion that can briefly outshine an entire galaxy, makes no sound at all. Or rather, it makes vibrations that have no air to travel through, no ears to hear them. When astronauts float outside their spacecraft, they work in this deep silence, with only the sounds of their own breathing and the hum of their equipment transmitted through their suits. Some find it peaceful, others find it unsettling. But there's something about that silence that feels sacred, doesn't there? As if the universe is holding its breath, as if all that vast activity is happening in a kind of cosmic meditation. Down here on Earth, we're surrounded by sound, wind and rain and voices and engines and birdsong. But up there in the space between worlds, there is only the quiet. And maybe tonight, as you drift towards sleep, you can imagine that silence, vast and clean and absolute, wrapping around you like a blanket, insulating you from every noise and worry, until all that remains is the gentle rhythm of your own breathing and the soft darkness behind your eyelids. Constellations are patterns we've drawn in the sky, connections between stars that have no real physical relationship to one another. The stars that form Orion's belt, for instance, are all at vastly different distances from Earth. They just happen to lie along the same line of sight from our perspective. It's like standing in a field and seeing a bird in a nearby tree, a cloud on the distant horizon, and the moon above, and deciding they're all connected because they momentarily align in your view. But the fact that constellations are essentially arbitrary, products of human imagination rather than cosmic design, doesn't make them less meaningful. We've been seeing these patterns and telling stories about them for thousands of years. They're part of our cultural heritage, our connection to our ancestors who looked up at the same sky and saw the same hunter, the same bear, the same swan. The stories change from culture to culture, but the impulse is universal. We want to find meaning in the lights above us, to connect them into narratives, to make the enormous sky feel a little more comprehensible, a little more like home. The constellations are humanity's way of hanging pictures on the walls of the cosmos, of decorating the infinite to make it feel more familiar, more ours. The night sky is darkest in the hours before dawn, in that deep well of night when the sun is as far below the horizon as it will get. This is when the most stars become visible, when the Milky Way shows itself most clearly, when the darkness is purest. Ancient peoples organized their lives around this darkness, waking and sleeping with the sun, experiencing the full depth of night in a way most of us modern humans never do. Our artificial lights have stolen much of the darkness from us, which seems like a blessing until you realize what we've lost, that profound connection to the cosmos, that nightly reminder of our planet's place in the universe. In light-polluted cities, you might see a few dozen stars at best. People have grown up never experiencing true darkness, never seeing the Milky Way, never understanding what our ancestors meant when they spoke of the countless stars. But the darkness is still there, waiting beyond the city limits, patient and timeless. And even if you can't get to it physically, you can imagine it. You can close your eyes and picture a sky so full of stars they seem to form clouds of light. A sky so dark that you can see nebulae with the naked eye. A sky that makes you feel simultaneously tiny and connected to everything, humbled and uplifted at once. Auroras dance in the polar skies when charged particles from the sun collide with Earth's atmosphere. The sun constantly streams these particles outward in what's called the solar wind, and when that wind encounters Earth's magnetic field, the field channels the particles toward the poles, where they interact with oxygen and nitrogen molecules, causing them to glow in shimmering curtains of green and red, and occasionally purple. These lights have inspired awe and mythology for as long as humans have lived in northern and southern latitudes. Some cultures saw them as spirits dancing, others as bridges to the afterlife, still others as omens or messages from the gods. The scientific explanation doesn't diminish their magic. If anything, knowing that you're watching the intersection of stellar wind and planetary magnetism, the visible evidence of invisible forces, makes them even more wondrous. The auroras remind us that Earth isn't isolated in space but constantly interacting with the sun, bathed in its influence, protected by magnetic fields that shield us from radiation while putting on an occasional light show as a side effect. Even if you've never seen an aurora in person, you can hold the knowledge of them in your mind as you drift toward sleep, imagining those flowing curtains of colored light, that silent cosmic dance happening right now over the poles, beauty born from the interplay of star and planet. The summer triangle isn't a constellation in the traditional sense, but rather an asterism, a recognizable pattern made from stars that belong to different constellations. It consists of 3 bright stars, Vega, Deneb and Altair, forming a large triangle that dominates the summer sky in the northern hemisphere. Vega is in the constellation Lyra, the lyre. Deneb is in Cygnus, the swan, and Altair is in Aquila, the eagle. These 3 stars are all relatively close to us, cosmically speaking, which is why they appear so bright. Vega is about 25 light-years away, Altair roughly 17, and Deneb, though much farther at around 1,500 light-years, is intrinsically so luminous that it still shines brilliantly despite the distance. In ancient Chinese astronomy, Vega and Altair were lovers separated by the Silver River, the Milky Way, allowed to meet only once a year when magpies formed a bridge across the sky. Even the heavens tell love stories, it seems. Even the stars can be woven into tales of longing and reunion. As you let yourself relax tonight, you might picture that triangle of light, hanging in the summer darkness, Three bright points forming a shape humans have recognized and named and told stories about, connecting our earthly experiences of geometry and narrative to the distant burning suns that care nothing for our patterns, and yet allow us to draw them anyway. Black holes may sound frightening, but they're simply the extreme endpoints of stellar evolution. What happens when the most massive stars run out of fuel and collapse in on themselves with such intensity that not even light can escape their gravitational pull? They're not cosmic vacuum cleaners, sucking up everything around them. They only affect objects that venture extremely close. If the Sun were somehow replaced with a black hole of equal mass, Earth would continue orbiting exactly as it does now. We just freeze in the absence of sunlight. But here's the strange beauty of black holes. They're not destroyers in any malicious sense. They're transformers. They warp space and time around themselves, creating regions where the normal rules of physics bend and break. Near a black hole, time runs slower, space curves back on itself, and the universe reveals its most extreme possibilities. Most black holes are far, far away, lurking in the centers of galaxies or wandering through interstellar space, remnants of ancient stars. The nearest known black hole is over 1,000 light-years from Earth. You're safe, more than safe, cushioned by distance and ordinary space. But isn't there something quietly profound about knowing they exist? About knowing that the universe contains places where matter becomes so dense, gravity so intense, that reality itself transforms into something stranger than any fiction. The Earth spins at about 1,000 miles per hour at the equator, hurtles around the Sun at 67,000 miles per hour, and the entire solar system orbits the center of the Milky Way at around 490,000 miles per hour. We're moving, always moving, through space at speeds that should terrify us, and yet we feel none of it. We feel perfectly still, lying in bed, settled and calm, because everything around us moves at the same speed. There's no wind of motion, no sense of velocity, just the gentle illusion of stillness. It's like being on an extraordinarily smooth train that's been traveling at constant speed for so long you've forgotten you're moving at all. And in that forgetting, there's peace. The universe is dynamic, constantly in motion, everything rotating and orbiting and drifting through space, and yet your experience right now is of perfect quiet of rest. You're hurtling through the cosmos at combined speeds that add up to more than 500,000 miles per hour, and simultaneously you're lying completely still, breathing slowly, perhaps on the edge of sleep. Both things are true. You contain multitudes of scale and perspective. You're both a tiny, still creature and a passenger on a planet racing through the void, and somehow both of those truths can coexist without contradiction, without disturbance. Light pollution is a relatively modern problem, but it's one we're becoming increasingly aware of. When the power went out in Los Angeles during an earthquake in 1994, the sudden darkness caused many residents to call emergency services about a strange, glowing cloud in the sky. They were seeing the Milky Way for the first time in their lives. We've gotten so accustomed to bright nights that true darkness feels alien, even threatening. But efforts are growing to preserve dark sky areas, places where people can still see the universe as our ancestors saw it, where the night sky reveals its full glory. There are now dark sky parks and reserves scattered around the world, protected zones where artificial light is minimized and the stars are allowed to shine through. Maybe someday you'll visit one, or maybe you'll simply step outside on a clear night far from city lights and look up, really look up, and let the enormity wash over you. But even if you never get to a truly dark sky, even if you live where the stars are few and faint, you still have access to the same sky. It's just hidden behind a veil of human light. The stars are still there, patient, waiting. Close your eyes now and see them anyway in your mind's eye, scattered across the darkness like diamonds on velvet, like snow suspended in midnight air, like all the hopes and dreams of everyone who's ever lived, hung up where they can shine forever. You're doing beautifully. There's no rush, nowhere you need to be, nothing you need to remember from what you're hearing. These are just gentle thoughts to accompany you, soft facts to cushion your mind as it releases the day. Let your breathing settle into its own natural rhythm. Feel the weight of your body against the surface beneath you. Notice how your muscles can let go a little more with each breath out. The night sky has been turning above our planet for billions of years, and it will continue turning long after this moment has passed. There's something deeply restful in that continuity, isn't there? You can simply let go and trust that the universe will keep spinning, the stars will keep shining, and you can rest. Red stars are cool stars, and blue stars are hot stars, which seems backward if you think of fire and the way red flames are hotter than yellow ones. But in space, the color of a star indicates its surface temperature. The coolest stars glow red, like embers in a dying fire, while the hottest burn blue-white, like the intense heart of a welding torch. Our sun is somewhere in the middle, a yellow-white star with a surface temperature of about 10,000 degrees Fahrenheit, which is cozy by stellar standards. The cooler red stars can last for trillions of years, burning their fuel so slowly that many of them will outlive the current age of the universe several times over. The hottest blue giants, by contrast, live fast and die young, burning through their fuel in just a few million years. There's an entire stellar ecology up there, different types of stars living different lengths of lives, each contributing to the cosmic story in its own way. When you see stars twinkling in the night sky, some of them are old beyond measure, some are newborns, and some are in the prime of their stellar lives. You're seeing a temporal snapshot of a galaxy constantly renewing itself, where death and birth happen on scales too vast and slow for us to perceive directly, but which we can understand and appreciate when we step back and consider the bigger picture. The Pleiades, also called the Seven Sisters, is a star cluster visible to the naked eye as a small, hazy patch in the constellation Taurus. Most people can see 6 stars in the cluster without optical aid, though it actually contains hundreds of stars, all born from the same cloud of gas about 100 million years ago. They're still relatively young as stars go, hot and blue and bright, and they're still loosely gravitationally bound to one another, drifting through space as a family. Many cultures have myths about the Pleiades. The Greeks saw them as 7 sisters pursued by Orion the hunter, while many Aboriginal Australian cultures have stories about 7 young women or sisters. In Japan, they're called Subaru, which means coming together or cluster, and they've become so culturally significant that a car company took the name and puts a stylized version of the cluster as its logo. There's something touching about a cluster of sibling stars, isn't there? Born together, traveling together through the cosmos, slowly drifting apart over millions of years but still recognizably a group, a family. It's a timescale that makes human families seem like the briefest flickering, yet the same impulse is there: connection, proximity, belonging. The Andromeda Galaxy is the farthest object you can see with your naked eye, appearing as a faint, fuzzy patch in the constellation Andromeda on dark nights. It's about 2.5 million light-years away, which means you're seeing it as it was 2.5 million years ago, when our ancestors were just beginning to use stone tools. The light that's hitting your eyes right now left Andromeda before humans were quite human, before we'd mastered fire or language, when we were still figuring out how to be the species we'd become. That light traveled across the vast emptiness between galaxies for all that time just to reach your eye on this particular night. And here's something even more remarkable. Andromeda is moving toward us. It's not receding like most galaxies but approaching, and in about 4 billion years it will collide with the Milky Way. Or rather, they'll merge, the 2 galaxies passing through each other, their stars so far apart that actual collisions will be rare, the whole process taking millions of years as the 2 structures tangle and eventually form a new, larger galaxy. But that's so far in the future that the sun will have already swelled into a red giant by then. For now, for your lifetime and countless generations before and after, Andromeda is simply a distant neighbor, a fellow city of stars, visible as a smudge of light if you know where to look, a reminder that our galaxy is not alone in the universe. Twilight is the gentle transition between day and night, but it actually comes in 3 distinct phases. Civil twilight is when the sun is just below the horizon and there's still plenty of light to see by. Nautical twilight is darker, when you can see the horizon at sea but need artificial light for most activities. Astronomical twilight is when the sky is finally dark enough that faint stars become visible and astronomers can begin their work. This gradual dimming happens because Earth's atmosphere scatters sunlight, bending it around the curve of the planet and softening the transition from light to dark. Without an atmosphere, night would fall as abruptly as flipping a switch, the way it does on the moon. But our air gives us this grace period, this slow fade, this time to adjust. Perhaps that's what you're experiencing now, a kind of mental twilight, a gentle dimming of thought and awareness, a gradual transition from waking to sleeping. There's no sharp boundary, just a soft gradient, and you can let yourself drift through these phases without marking exactly where one ends and another begins. The universe gives us time to adjust to darkness, to transition slowly, and you can give yourself that same kindness, letting sleep approach at its own pace in its own time. Meteor showers have names based on the constellation from which they appear to radiate. The Perseids come from Perseus, the Geminids from Gemini, the Leonids from Leo. This radiant point is really just a trick of perspective. The meteors are actually moving on parallel paths, but they appear to spread out from a single point in the same way that parallel railroad tracks appear to converge at a distant point. Each meteor shower happens when Earth passes through the debris trail left by a comet, and they occur at the same time every year because Earth's orbit is constant. You can mark your calendar by meteor showers. The Perseids in August, the Geminids in December, the Lyrids in April. They're like cosmic holidays, regular occurrences in the night sky, celestial events that connect us to the ancient comets that shed the dust we're seeing burn up. Some of these comets haven't been near the sun in centuries, but they left debris trails that persist, orbiting the sun on their own, waiting for Earth to pass through and put on a show. It's like walking through a room where someone once scattered confetti, long after they've left, and feeling those paper pieces brush against your face, reminders of a celebration you weren't present for but can still experience the aftermath of. The zodiac constellations are simply the constellations that lie along the ecliptic, the path the sun appears to trace through the sky over the course of a year. Because the planets also orbit in roughly the same plane, they too pass through these 12 constellations, which is why astrology assigns significance to which constellation the sun or planets were in at the time of your birth. From a scientific standpoint, the alignments are accidents of perspective, but they've been culturally significant for thousands of years. Ancient peoples watched the sky carefully, noting which constellations the sun rose in front of at different times of year, and they built calendars around these observations. The zodiac was functional long before it was mystical. It was a way of tracking time, of predicting when to plant crops and when to harvest. Over millennia, these practical observations became layered with meaning and mythology, until the zodiac became a language of personality and prediction. Whether you find meaning in astrological interpretations or see them as charming cultural artifacts, the constellations themselves remain ancient patterns in the sky that humans have been watching and naming and weaving stories around for as long as we've been capable of telling stories at all. The sun contains 99.86% of all the mass in our solar system. All the planets, moons, asteroids, comets, dust, and debris combined make up less than a fraction of a percent. We live on a tiny speck orbiting an enormous ball of fire, held in place by its gravity, warmed by its light, utterly dependent on its steady burning. And yet the sun itself is just one star among hundreds of billions, utterly ordinary, neither particularly large nor especially small, not unusually hot or cool or bright. It's a middle-aged, middle-of-the-road, thoroughly average star, and that averageness is part of what makes our existence possible. Extreme stars don't last long or don't have stable habitable zones around them. We need ordinary to thrive. There's something quietly reassuring about that, about being held in the gravitational embrace of a very normal star, about our home being neither special nor doomed by extremity, just comfortably, sustainably average. As you settle into sleep tonight, you can hold that thought. You live in a system defined by balance and moderation, where the star at the center is stable enough to have nurtured life for billions of years, and will continue to do so for billions more. Nebulae are vast clouds of gas and dust, the birthplaces and graveyards of stars, glowing with colors that seem impossible, deep reds and blues and greens that photographs capture in breathtaking detail. Some nebulae are illuminated by nearby stars, their light causing the gas to fluoresce like neon signs. Others are dark, visible only as silhouettes against brighter backgrounds, shadows in space. The Orion Nebula is one of the most studied objects in the sky, a stellar nursery where new stars are forming right now, where gravity is condensing clouds of hydrogen into objects that will soon ignite and become new suns. If you look at Orion's belt and follow the line of stars hanging below it, Orion's sword, the middle star is actually the nebula, visible as a hazy smudge even with the naked eye. Inside that small patch of light, entire solar systems are coming into being. Planets are coalescing from disks of dust. The future is being built in slow motion. Nebulae remind us that the universe is not static but constantly creating, constantly recycling its material, constantly turning endings into new beginnings. The atoms in your body were once part of a nebula, drifting in space, and someday, billions of years from now, they'll be part of one again, scattered and waiting to become something new. The Doppler effect shifts the color of starlight based on whether a star is moving toward or away from us. Light from stars moving away shifts toward the red end of the spectrum, while light from stars approaching shifts toward blue. This is how we know the universe is expanding. Distant galaxies show red-shifted light, meaning they're moving away from us, and the farther away they are, the faster they're receding. It's one of the most profound discoveries in astronomy, this realization that the entire universe is in motion, that space itself is stretching like a fabric being pulled in all directions at once. But here's the gentle part. This expansion happens on cosmic scales, between galaxy clusters separated by millions or billions of light years. It doesn't affect your daily life, doesn't pull apart the Earth or the solar system or even our galaxy. On local scales, gravity holds everything together just fine. The expansion of the universe is real and ongoing, but it's happening so far away on such vast scales that it's irrelevant to anything in your immediate experience. You can rest easy knowing that while the cosmos expands, your world remains stable, held together by forces that are more than sufficient to keep everything in place, to keep you safe and grounded and connected to the planet beneath you. Cosmic rays are high-energy particles, mostly protons, that zip through space at nearly the speed of light. They come from supernovae, from black holes, from the sun, from sources we haven't fully identified, and they constantly bombard Earth from all directions. Our atmosphere and magnetic field protect us from most of them, but a few make it through, and they pass through your body all the time, several cosmic rays per second, on average. You're being very gently irradiated by the universe at every moment, particles that have traveled across light years of space to pass through you and continue on their way into the Earth or back out into space. It sounds alarming but isn't. The dose is tiny, far less than you get from natural background radiation or a cross-country flight. Mostly it's just remarkable to think about. Right now, as you rest, particles that may have originated in a supernova explosion thousands of light years away are streaming through your body, silent and invisible, connecting you physically to distant cosmic events. You're not separate from the universe, not observing it from outside. You're porous to it, permeable, part of the flow of matter and energy that moves through everything. The Great Red Spot on Jupiter is a storm that's been raging for at least 350 years, possibly much longer. It's a high-pressure region in Jupiter's atmosphere, an anticyclone larger than Earth, with winds howling at hundreds of miles per hour. And it just keeps going year after year, decade after decade, century after century. It's shrinking gradually. Observations over the past century show it getting smaller. But it's still enormous, still spinning, still very much active. There's something almost soothing about the idea of a storm so stable, so persistent, that it becomes a permanent feature rather than a temporary event. On Earth, our storms last days or weeks at most. On Jupiter, a storm can outlast empires, outlast entire human civilizations. It's been swirling since before the Industrial Revolution, before the founding of nations, watched by astronomers through increasingly powerful telescopes for longer than your country has existed. And it will likely continue long after you and I are gone, this great swirl of rust-colored clouds in Jupiter's alien sky. A reminder that what seems chaotic and violent can also be enduring, that even turbulence can find a kind of equilibrium and persist almost indefinitely. Starlight is almost unimaginably old by the time it becomes light in the first place. The light you see from the sun takes about 8 minutes to reach Earth, but the photons themselves were created in the sun's core hundreds of thousands of years ago. The sun's core is a nuclear furnace, fusing hydrogen into helium, and that fusion releases energy in the form of photons. But those photons are immediately absorbed and re-emitted by the dense matter surrounding the core. and they bounce around randomly inside the sun for a very, very long time, somewhere between 170,000 and several million years, depending on the estimates, before they finally reach the surface and stream out into space. The light that's warming your face on a sunny day was born deep inside the sun before recorded human history began, slowly, randomly bouncing its way outward through unfathomable density, until it finally broke free and made the 8-minute journey to your eyes. Every photon has a story, a long and chaotic history, and all that history culminates in a tiny moment of warmth or illumination, a brief interaction with your skin or eyes before the photon continues on its way out into space, carrying its energy farther into the cosmos. The Oort cloud is a theoretical shell of icy objects surrounding our solar system at an immense distance, perhaps a light year or more from the sun. It's so far away that we've never directly observed it, but we infer its existence from the long-period comets that occasionally fall inward toward the sun from that direction, taking thousands or millions of years to complete a single orbit. The Oort cloud may contain billions or even trillions of comets, icy remnants from the solar system's formation, scattered to the outermost reaches by gravitational interactions with the giant planets. It's the edge of the sun's gravitational influence, the farthest extent of our solar system, and beyond it lies true interstellar space, the void between stars. But even that void isn't empty. It's filled with the interstellar medium, with magnetic fields, with cosmic rays, with rogue planets that were ejected from their star systems and now wander in the dark. The universe has no true edges, no clear boundaries. Everything fades gradually into everything else. The solar system doesn't end at a wall, but tapers off in density and influence until you're simply in interstellar space without ever crossing a definite line. Perhaps sleep is like that too. Not a border you cross, but a gradient you slide along, awareness fading so gently that you can't pinpoint the moment it becomes something else. Binary star systems are more common than single stars like our sun. Most stars have at least one companion, and they orbit each other, bound by mutual gravity, dancing through space in partnership. Some binaries are so close they orbit in hours or days, while others are separated by distances measured in thousands of astronomical units, and take thousands of years to complete an orbit. From a planet orbiting a binary system, you'd see two suns in the sky, sometimes rising and setting separately, sometimes appearing together. The sunsets would be different colors, the shadows more complex, the seasons strange and unpredictable as the two stars' influences combined in intricate ways. It's a reminder that our solar system's configuration, one star, planets neatly orbiting, is just one possibility among many. The universe is creative in its arrangements, trying out different configurations, different dances. And while binary stars sound exotic, they're actually the norm. Our single sun is the unusual case. We're the outliers, the exception, living in a system that's simpler than average, more solitary, and that solitude has shaped the rhythms of our world in ways we rarely think about. One sun, one day-night cycle, one set of seasons, one source of warmth and light. It's enough. It's more than enough. It's all we've ever known, and it's created the conditions for life and consciousness, and this very moment, where you can contemplate the fact that other systems are different and feel a kind of gratitude for the simplicity we were given. The Kuiper Belt is a region beyond Neptune filled with icy bodies, dwarf planets, and the remnants of the solar system's formation. Pluto lives here, along with other dwarf planets like Eris, Makemake, and Haumea. These are cold, distant worlds, receiving only a tiny fraction of the sun's light, their surfaces frozen to temperatures just a few dozen degrees above absolute zero. They're ancient, largely unchanged since the early days of the solar system, time capsules preserving the conditions and materials that existed when the planets were forming. NASA's New Horizons spacecraft flew past Pluto in 2015, sending back images that revealed an unexpectedly complex world. Mountains made of water ice as hard as rock, plains of frozen nitrogen, possible subsurface oceans. Even at the edge of the solar system, there's beauty and complexity, worlds worth studying and wondering about. The Kuiper Belt reminds us that the solar system is vast, that the planets we learned about in school are just the beginning, that there are thousands or millions of objects out there, each with its own story, most of which we'll never visit or study in detail, but which exist nonetheless, silently orbiting, patient and cold and real. Light years are a measure of distance, not time, though the name suggests otherwise. 1 light year is the distance light travels in 1 year at its constant speed of about 186,000 miles per second, which works out to roughly 5.88 trillion miles. It's a unit created for convenience because the distances between stars are so large that conventional units become unwieldy. Saying a star is 25 light-years away is easier than saying it's 147 trillion miles away. But using time to measure distance is also poetically appropriate, because in astronomy, distance and time are inextricably linked. To see far is to see into the past. The light year as a unit acknowledges this relationship, building it into the measurement itself. When astronomers talk about looking at galaxies billions of light-years away, they're talking about seeing light that's been traveling for billions of years, about observing the universe as it was when that light began its journey. The most distant objects we can see are showing us the universe in its infancy, just a few 100 million years after the Big Bang. Distance becomes time, becomes history. Looking out becomes looking back. And here you are right now, neither looking particularly far into space nor back into time, simply existing in the present moment, in your body, in this room, in this small slice of space-time that you occupy, and that's its own kind of miracle. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like lighthouse beams, and if Earth happens to be in the path, we detect regular pulses of radio waves, X-rays, or gamma rays. The pulses are extraordinarily regular. Some pulsars tick with more precision than atomic clocks. When they were first discovered in 1967, the regularity was so unexpected that astronomers briefly considered whether they might be signals from alien civilizations, and they jokingly dubbed the first one LGM-1 for Little Green Men. But the explanation turned out to be even stranger than aliens. These are the collapsed cores of massive stars, objects where the mass of our sun is compressed into a sphere just a few miles across, spinning at rates of up to hundreds of times per second. They're made of neutrons packed so tightly that a teaspoon of neutron star material would weigh billions of tons. They're among the most extreme objects in the universe, matter pushed to limits we can barely comprehend, and they're out there right now, spinning and pulsing, sending their signals out into the void. Most of those signals pass through Earth unnoticed, invisible and undetectable without specialized equipment. But they're there, washing over you constantly, cosmic lighthouse beams that mark the locations of ancient stellar catastrophes, now turned into precision timekeepers scattered across the galaxy. Saturn's rings are made of countless particles of ice and rock, ranging from grains of sand to chunks the size of houses, all orbiting the planet in a flat disk. They're surprisingly thin, in places only about 30 feet thick, despite being over 170,000 miles in diameter. If you could shrink the rings down to the size of a football field, they'd be thinner than a razor blade. We don't know exactly how old they are. They might be ancient, dating back to the formation of the solar system, or they might be relatively young, perhaps the remains of a comet or moon that wandered too close and was torn apart by Saturn's gravity. The rings won't last forever. They're slowly falling into the planet, raining down into Saturn's atmosphere, and in another 100 million years or so, they'll be gone. But right now, in this brief window of cosmic time, they're there, beautiful and intricate, visible through even a modest telescope as a delicate structure encircling the giant planet. It's extraordinary luck, really, that we exist at the right time to see Saturn as a ringed world. In the deep past, the rings might not have been there. In the far future, they won't be. But now, in this moment, this era, they shine, and we can look at them and marvel. Let's pause again for just a moment. You're still here, still listening, or perhaps you're drifting at the edges of awareness now, hovering in that soft space between waking and dreaming. That's exactly where you should be. There's no test later, no need to remember any of this. These words are just companions, gentle presences to keep you company as your mind releases its grip on the day. The universe is vast, but you don't have to hold it all. You just have to rest. Let your thoughts become like stars, distant, quiet, glimmering softly but not demanding anything from you. Breathe, settle, let go a little more. Tidal forces are caused by the difference in gravitational pull across an object. The moon pulls on the side of Earth facing it more strongly than it pulls on the far side, and this difference creates bulges in Earth's oceans, what we experience as tides. But tidal forces work both ways. Earth's gravity creates tidal forces on the moon too, and over billions of years, these forces have slowed the moon's rotation until it became tidally locked, rotating at exactly the same rate it orbits Earth, which is why we always see the same face of the moon. The far side remains hidden from us, not because it's dark. It gets just as much sunlight as the near side, but because the moon's rotation and orbit are perfectly synchronized. Tidal locking is common in the universe. Most moons eventually become locked to their planets. Some planets are tidally locked to their stars, with one side in perpetual daylight and the other in eternal night. It's gravity's way of settling systems into stable configurations, of turning dynamic motion into predictable patterns. There's a metaphor there, perhaps, about finding balance, about how forces that initially cause disruption can eventually create equilibrium, how chaos settles into rhythm given enough time. Voyager 1 and Voyager 2 are humanity's most distant emissaries, spacecraft launched in 1977 that explored Jupiter, Saturn, and beyond before heading out into interstellar space. Voyager 1 is currently over 15 billion miles from Earth, so far away that radio signals traveling at the speed of light take more than 22 hours to reach it. Both spacecraft carry golden records, gold-plated phonograph records containing sounds and images intended to represent the diversity of life and culture on Earth. There are greetings in 55 languages, music from different cultures and eras, sounds of nature, pictures of human anatomy and activity. It's a message in a bottle cast into the cosmic ocean, an act of hope and communication directed at unknown recipients who may never exist, or, if they do, won't find the records for millions or billions of years. The Voyagers are powered by slowly decaying plutonium, and their instruments will eventually fall silent in the next decade or so. But the spacecraft themselves will continue coasting through space essentially forever, silent monuments to human curiosity and ambition. They'll outlast our civilization, our species, possibly our planet, drifting through the galaxy long after everything we know is gone, carrying that little golden record with its sounds of Earth. Waves crashing, whales singing a mother's kiss, Beethoven and Chuck Berry, thunder and laughter and wind. It's beautiful and melancholy at once, this gesture of reaching out into the vastness, this refusal to remain silent even in the face of cosmic indifference. The zodiacal light is a faint, diffuse glow visible in the night sky, extending along the ecliptic, the path the sun and planets follow. It's caused by sunlight reflecting off tiny dust particles in the plane of the solar system, remnants of comets and asteroid collisions. It's best visible just after sunset or just before sunrise, a soft pyramid of light rising from the horizon. Most people have never seen it because it's so faint that any light pollution washes it out. But in truly dark skies, it's a common sight, a gentle reminder that space isn't perfectly empty, that the solar system contains not just planets and moons but also vast quantities of dust, spread thin but present, catching the sun's light and scattering it in our direction. The dust is slowly spiraling inward toward the sun, pulled by the Poynting-Robertson effect, a subtle interaction between light pressure and orbital mechanics. Eventually, in millions of years, it will fall into the sun, but new dust is constantly being created by collisions and comet outgassing. So the zodiacal light persists, a self-renewing glow that's been visible for as long as humans have had eyes to see it, though often mistaken for the last remnants of twilight or the approaching dawn. Variable stars change in brightness over time, pulsing brighter and dimmer in regular or irregular cycles. Some, like Cepheid variables, pulse because they physically expand and contract, swelling and shrinking in a rhythmic cycle determined by their internal structure. Others, like eclipsing binaries, dim periodically because a companion star passes in front of them from our perspective, temporarily blocking the light. Still others vary unpredictably, flaring or dimming due to stellar activity like massive starspots or eruptions. Cepheid variables are particularly important in astronomy because their pulsation period is directly related to their intrinsic brightness. The longer the period, the brighter the star. This means that by measuring how long a cepheid takes to pulse, you can figure out how bright it really is, and by comparing that to how bright it appears from Earth, you can calculate its distance. Cepheids are standard candles that allow us to measure distances across the galaxy and even to nearby galaxies, building up a cosmic distance ladder that reaches millions of light-years into space. These pulsing stars, breathing in and out with periods of days or weeks, serve as measuring sticks for the universe, their rhythmic variations encoding information about the scale and structure of the cosmos. The Hubble Space Telescope, launched in 1990, has revolutionized our understanding of the universe by observing from above Earth's atmosphere, which blurs and blocks much of the light from space. Hubble has taken some of the most iconic images in astronomy, the pillars of creation, the Hubble Deep Field, countless nebulae and galaxies captured in vivid detail. It's been serviced by astronauts multiple times, with new instruments installed and old ones repaired, keeping it operational far longer than originally planned. As of now, it's still working, still sending back images, though it's aging and will eventually be replaced. Its successor, the James Webb Space Telescope, launched in 2021, observes primarily in infrared light, seeing through dust clouds and looking even farther back in time to the earliest galaxies. Together, these observatories are expanding human knowledge, revealing the universe in wavelengths our eyes can't see, finding planets around distant stars, measuring the expansion rate of the universe, discovering that the expansion is accelerating, driven by mysterious dark energy. Telescopes are our eyes on the cosmos, extending our vision across billions of light-years, allowing minds that evolved on an African savanna to comprehend structures that span the observable universe. It's one of humanity's greatest achievements, this determination to see and understand, to build instruments that overcome our limitations and reveal what was previously hidden. Earth's atmosphere creates the colors of sunrise and sunset by scattering light. When the sun is low on the horizon, its light passes through more atmosphere than when it's directly overhead, and the atmosphere scatters the shorter blue wavelengths away, leaving the longer red and orange wavelengths to reach your eyes. This is why the sky is blue during the day, you're seeing the scattered blue light, and why the sun looks red at sunrise and sunset. On the moon, which has no atmosphere, the sun is harsh white, and the sky is black even in daytime because there's no air to scatter the light. The soft colors of our sunrises and sunsets are gifts from our atmosphere, beautiful side effects of physics. Every sunset is unique because the atmosphere is never exactly the same. Different amounts of dust, moisture, and pollution create endless variations in color and intensity. The most dramatic sunsets often follow volcanic eruptions, when ash and sulfur dioxide particles in the upper atmosphere scatter light in unusual ways, creating deep reds and purples that can last for months or even years. The sky is a canvas, and the sun and atmosphere collaborate to paint it twice a day, a daily gift of beauty that we often take for granted but which has inspired artists and poets for as long as humans have had the capacity for aesthetic appreciation. Gravitational lensing occurs when a massive object like a galaxy cluster bends the fabric of space-time around it, and light from more distant objects follows that curve, creating distorted, magnified, or multiple images of the background object. Einstein predicted this effect in his general theory of relativity, and it's been confirmed countless times. Sometimes a distant galaxy directly behind a massive foreground galaxy will be smeared into a ring, an Einstein ring, surrounding the closer galaxy. Sometimes the lensing creates multiple images of the same quasar or galaxy, scattered around the lens. Gravitational lensing is now used as a tool, allowing astronomers to study distant objects that would otherwise be too faint to see, and to map the distribution of dark matter in galaxy clusters by observing how they bend light. It's a beautiful vindication of Einstein's insight that gravity isn't a force in the traditional sense, but rather a curvature of space-time, and that curvature affects everything, including light. The universe bends itself, warps itself, and in doing so reveals things that would otherwise remain hidden. Imperfections in the cosmic lens give us clearer vision, not despite their distortions but because of them. Exoplanets, planets orbiting stars other than our Sun, were purely theoretical until the 1990s, but we've now confirmed thousands of them, with thousands more candidates waiting for verification. They come in a bewildering variety. Hot Jupiters that orbit closer to their stars than Mercury does to our Sun, super-Earths with masses several times our planets, water worlds covered entirely in deep oceans, lava planets with surfaces hot enough to melt rock, rogue planets drifting through space without any star at all. Some orbit binary stars. Some are tidally locked. Some may have conditions suitable for life, though we haven't yet found definitive evidence of biology beyond Earth. The sheer diversity is humbling and exciting. The universe is far more creative than our imagination anticipated. The discovery of exoplanets has transformed the question, are we alone? From philosophy to science, turning it into something we can actually investigate with telescopes and spectroscopy. We can analyze the atmospheres of some exoplanets by watching how starlight filters through them during transits, searching for chemical signatures that might indicate life. It's early days yet, but the tools are improving and the search continues. Somewhere among those thousands of confirmed worlds, there may be one where, at this very moment, someone is looking up at their sky and wondering if they're alone. Spacecraft that travel to the outer solar system use gravity assists, slingshotting around planets to gain speed without using fuel. Voyager 2 used gravity assists from Jupiter, Saturn, Uranus, and Neptune, effectively stealing a tiny bit of each planet's orbital momentum to accelerate itself. This technique allows us to send spacecraft to destinations that would otherwise be unreachable given the limitations of our rockets and fuel capacity. It's a beautiful application of orbital mechanics, using the natural movements of planets to accomplish what we couldn't do with brute force. The planets barely notice. The momentum transferred is so small that it has no measurable effect on their orbits. But for the spacecraft, it makes all the difference. Sometimes the most elegant solutions aren't about power but about working with what's already there, about finding pathways through the existing structure of reality rather than forcing your way through. The gravity assist is physics as partnership, a collaboration between human engineering and the natural dynamics of the solar system. Comets are often described as dirty snowballs, lumps of ice and rock that spend most of their time in the cold outer reaches of the solar system, but occasionally swing in close to the Sun, where the ice begins to sublimate, turning directly from solid to gas, and creating the characteristic glowing coma and streaming tail. The tail always points away from the Sun, pushed by the solar wind and radiation pressure, not trailing behind the comet's motion. This means that as a comet rounds the Sun and heads back out, its tail actually precedes it, pointing forward. Comets are ancient, largely unchanged since the solar system's formation, and they may have delivered water and organic molecules to the early Earth, seeding our planet with the ingredients for life. Some comets are regular visitors, like Halley's Comet, which swings by every 75 years or so. Others are long-period comets that take thousands or millions of years to orbit, visitors we see only once in all of human history. There's something poignant about a comet, a wanderer, spending most of its existence in cold darkness, with only brief moments of warmth and visibility before returning to the outer dark. And yet those brief moments are spectacular, bright enough to be visible even in daylight sometimes, inspiring awe and fear throughout human history, seen as omens and portents, now understood as remnants of creation, messengers from the ancient past. The speed of light is not just the speed at which light travels but a fundamental constant of the universe, the maximum speed at which information or causality can propagate. Nothing with mass can reach light speed because as you accelerate, your mass effectively increases, requiring ever more energy to accelerate further, and you'd need infinite energy to actually reach light speed. Light itself travels at this speed because photons have no mass. But the speed of light also determines how quickly cause can lead to effect, how fast influences can spread. When something happens on the Sun, a flare and eruption, we don't see it for 8 minutes and Earth's environment doesn't respond until the particles and radiation arrive, minutes to days later. The universe has a built-in delay, a speed limit that ensures that distant events take time to affect us, that there's always a buffer, a space between cause and consequence. In a strange way, this is comforting. It means the universe is not instantaneous, not overwhelming in its immediacy. There's time to process, time for light to travel, time between one moment and the next. Even the cosmos respects the need for transition, for gradual change, for the gentle unfolding of events rather than everything happening all at once. Dark matter makes up about 85% of all matter in the universe, but we can't see it directly because it doesn't emit, absorb, or reflect light. We know it exists because of its gravitational effects. Galaxies rotate too fast to be held together by the mass of visible stars alone, and galaxy clusters bend light more than their visible matter accounts for. Something invisible but massive is out there, threading through and around galaxies, providing the gravitational scaffolding that holds the visible universe together. We don't yet know what dark matter is. It's not made of atoms like ordinary matter, and it interacts with regular matter almost exclusively through gravity. Various experiments are searching for dark matter particles, and theorists are proposing candidates, but so far it remains mysterious, a reminder that for all our knowledge, we still don't understand most of the universe's contents. There's something humbling and strangely reassuring about that, about knowing there are fundamental mysteries still unsolved, that the universe can still surprise us, that we haven't figured everything out and perhaps never will. The darkness holds secrets, but those secrets don't threaten us. They simply wait, patient and silent, for minds curious enough and clever enough to eventually decode them, or at least to come a bit closer to understanding. Supernovae are among the most energetic events in the universe, the explosive death of a massive star, releasing in a few seconds as much energy as the sun will emit over its entire 10 billion-year lifetime. The explosion is so bright that a supernova in our galaxy can briefly be visible during the day, rivaling the brightness of the moon. Historical records from various cultures describe guest stars that suddenly appeared and then faded over weeks or months. These were supernovae. The supernova remnants are still visible today as expanding shells of gas, like the Crab Nebula, which is the remnant of a supernova that was observed and recorded by Chinese and Arab astronomers in 1054 AD. Supernovae are both endings and beginnings. They destroy the star that created them, but they also scatter heavy elements into space, enriching the interstellar medium with the building blocks of planets and life. They trigger the collapse of nearby gas clouds, initiating new star formation. They leave behind neutron stars or black holes, exotic objects that carry forward a ghost of the original star. Supernovae are the universe's way of recycling, of returning matter to the cosmic ecosystem, of ensuring that endings feed into new beginnings in an endless cycle of creation and destruction. Space is cold, really cold, because there's so little matter to hold heat. Temperature is a measure of how fast particles are moving, but in the vacuum of space, there are so few particles that the concept of temperature becomes almost meaningless. Objects in space lose heat through radiation, gradually cooling toward the cosmic background temperature of about 2.7 Kelvin, just a couple degrees above absolute zero. But in sunlight, objects heat up quickly because there's no atmosphere to distribute the heat. This is why astronauts need spacesuits with careful temperature regulation. One side can be baking in direct sunlight, while the other side is frozen in shadow. The suit has to balance these extremes, protecting the human inside from conditions that would otherwise be lethal. Space is a place of extremes, of harsh contrasts, but it's also empty enough and silent enough and dark enough that it can feel almost peaceful if you're safely inside a spacecraft, looking out at the stars, watching Earth turn below you, seeing the thin blue line of atmosphere that separates the habitable world from the void. That fragile boundary is all that stands between life and emptiness, and yet it's held, robust and resilient, for billions of years. Red giants are what stars like our Sun become near the end of their lives, when they've exhausted the hydrogen in their cores and begin fusing helium into carbon and oxygen. The star swells enormously, becoming hundreds of times larger, its outer layers expanding and cooling, turning red. Our Sun will eventually become a red giant, swelling to engulf Mercury and Venus, possibly even reaching Earth's orbit. But that's billions of years away. The Sun is only about halfway through its current stable phase. When it does happen, Earth will long since have become uninhabitable for other reasons. As the sun ages, it slowly brightens, and in another billion years or so, Earth will be too hot for liquid water. But all of this is so far in the future that it's not worth worrying about. Entire new evolutionary lineages could rise and fall in the time between now and then. The sun's eventual death is inevitable but distant, a reminder that nothing lasts forever, but that sometimes temporary means billions of years, which is as close to forever as makes no practical difference to creatures who live for decades. Globular clusters are dense, spherical collections of hundreds of thousands or even millions of stars, orbiting in the halos of galaxies. The stars in globular clusters are very old, among the oldest in the universe, dating back to the early formation of their host galaxies. They're gravitationally bound so tightly that stars within the cluster can pass very close to one another, sometimes even capturing each other into binary systems. If you could stand on a planet orbiting a star in the core of a globular cluster, the night sky would be breathtaking. Thousands of stars visible, closer and brighter than anything we see from Earth, the sky never truly dark. But you'd also be bombarded by radiation from all those nearby stars, and close stellar encounters might destabilize planetary orbits over time, making long-term habitability unlikely. Globular clusters are beautiful from afar. Through a telescope, they look like jeweled spheres, dense cores surrounded by gradually thinning halos of stars. They're relics from the early universe, fossils preserved in stellar form, and studying them helps us understand how galaxies formed and evolved over cosmic time. The Great Attractor is a gravitational anomaly in intergalactic space, a region where mass seems to be concentrated in ways that are pulling our galaxy, and many others toward it at speeds of hundreds of kilometers per second. It lies in the direction of the constellations Hydra and Centaurus, partially hidden behind the Milky Way's own disk, which makes it hard to observe directly. We're not sure exactly what the Great Attractor is. It seems to be a massive concentration of galaxies, possibly a supercluster, pulling on our local group through gravity. But beyond the Great Attractor is something even larger, the Shapley supercluster, an even more massive structure that may be the true source of the motion. We're being pulled, slowly and inexorably, toward this distant concentration of mass, along with thousands of other galaxies all flowing like rivers toward the ocean. But the distances are so vast, and the speeds, though high by earthly standards, so slow cosmically that this motion has no practical effect on our lives or even on Earth's future. It's simply a fact of cosmic dynamics. Everything is moving, flowing, being pulled by gravity into patterns and streams that span hundreds of millions of light years. We're part of a vast cosmic current, and we always have been, flowing along with the rest of the local universe toward distant, dimly understood concentrations of mass and gravity. White dwarfs are what stars like the Sun become after their red giant phase, when they've shed their outer layers and left behind a hot, dense core about the size of Earth but with a mass comparable to the Sun's. They're incredibly dense. A teaspoon of white dwarf material would weigh several tons. They no longer undergo fusion. They're simply cooling embers glowing from residual heat, gradually fading over trillions of years. Eventually they'll become black dwarfs, cold, dark, inert objects. But the universe isn't old enough yet for any black dwarfs to exist. Every white dwarf we can see is still glowing, still warm, still radiating the last of its stored energy into space. Some white dwarfs are in binary systems, pulling matter off a companion star, and if they accumulate enough mass, they can explode as Type Ia supernovae, spectacular events that are so consistent in brightness they're used as standard candles to measure cosmic distances. White dwarfs are the final fate of most stars, including our Sun. Not a violent ending but a gentle fading, a slow dimming over timescales so long that they're essentially eternal by any meaningful standard. It's an ending, yes, but a quiet one, and there's something peaceful about that, about knowing that not everything ends in catastrophe, that sometimes things just slowly, gradually wind down, cooling and dimming until they're indistinguishable from the darkness, but taking so long to do it that the process itself becomes a kind of permanence. You're doing wonderfully. We're more than halfway through this gentle journey now. There's no destination, of course. We're simply wandering together through ideas and images, letting them wash over you without needing to hold on to any of them. If you've drifted off already, that's perfect. If you're still listening, that's perfect too. There's no right way to do this. The night sky doesn't ask anything of you. It doesn't need you to understand it or remember it or do anything with it. It simply exists, vast and patient, and you can exist alongside it, small and temporary but no less real, no less part of the whole. Brown dwarfs are objects that are too massive to be planets but not massive enough to sustain hydrogen fusion and become true stars. They're sometimes called failed stars, though that's a bit unfair. They're simply objects in an in-between category, glowing faintly from the heat of their formation and from fusion of deuterium, a heavy isotope of hydrogen, but never quite achieving the conditions needed for sustained fusion of ordinary hydrogen. They're dim and cool, often only a few hundred degrees warmer than Jupiter, and they're surprisingly common. We've discovered thousands of them, and there may be billions in the galaxy, drifting unseen because they emit so little light. Brown dwarfs blur the distinction between planets and stars, occupying a middle ground that reminds us that nature doesn't always fit into neat categories. The universe is full of these in-between things, objects that challenge our definitions and expand our understanding. They're not quite one thing or another, and that's okay. They exist as they are, serving as reminders that boundaries are often more about our need to categorize than about any fundamental division in nature itself. The Antarctic night sky, during the long polar night when the sun doesn't rise for months, offers some of the clearest, darkest views available from Earth. The air is cold and dry, with very little moisture to blur the stars, and the lack of light pollution in the interior of the continent creates conditions unmatched almost anywhere else. Research stations in Antarctica take advantage of these conditions, hosting telescopes and detectors that study the cosmic microwave background radiation, search for meteorites on the ice, and observe the southern sky with exceptional clarity. There's something austere and beautiful about astronomy in Antarctica. The harshness of the environment, the isolation, the months of darkness, all in service of seeing more clearly, of pushing back the fog of atmosphere and light pollution to glimpse the universe in sharper detail. It's a reminder that sometimes clarity requires sacrifice, that to see more, we have to remove ourselves from comfort, to seek out the difficult places where conditions align to offer perspectives unavailable anywhere else. But you don't need to go to Antarctica to appreciate the night sky. Even from a backyard, even through clouds and light pollution, the fact of the stars remains. They're up there, whether you can see them clearly or not, and knowing that there is sometimes enough. Neutron stars are extraordinarily dense, roughly 1.4 times the mass of the Sun compressed into a sphere only about 12 miles across. They're made almost entirely of neutrons, hence the name, packed together so tightly that the entire star is essentially one giant atomic nucleus. The gravity at the surface is about 2 billion times stronger than Earth's. If you dropped an object from a height of 1 meter above the surface of a neutron star, it would hit the ground at a significant fraction of the speed of light. The conditions are so extreme that normal matter is crushed into states that we can barely model, even theoretically. Neutron stars are the leftovers of supernova explosions, the collapsed cores of massive stars, and they are among the most extreme objects in the universe. Some are pulsars, beaming radiation into space as they spin. Others are magnetars, with magnetic fields trillions of times stronger than Earth's, so intense that they distort the electron clouds of atoms and could be lethal from thousands of miles away. These objects sound terrifying, but they're also fascinating, examples of what the universe can create when physics is pushed to its limits. And they're far away, safely distant, their extreme nature confined to small regions of space, allowing us to study them without being threatened by them, to appreciate their strangeness from the comfort of our stable, temperate planet. Solar eclipses occur when the moon passes between Earth and the sun, blocking the sun's light. Total solar eclipses, where the moon completely covers the sun's disk, are rare and spectacular events. The sky darkens to twilight, stars become visible, and the sun's corona, normally invisible against the bright disk, blooms into view as a delicate halo of light. It's an astonishing cosmic coincidence that the moon and sun appear almost exactly the same size in our sky. The Sun is about 400 times larger than the Moon, but it's also about 400 times farther away, so they appear nearly identical in angular size. This won't always be true. As the Moon slowly drifts away from Earth, it will eventually be too small to completely cover the Sun, and total solar eclipses will no longer be possible. But for now, for this brief window of geological time, we're alive during an era when total solar eclipses happen, and they are among the most awe-inspiring natural phenomena you can witness. Those who have seen totality describe it as life-changing, a visceral reminder of the cosmic dance we're part of, the precision of orbits, the interplay of light and shadow, the way the universe can align just so to create a moment of perfect, eerie beauty. The Horsehead Nebula is one of the most recognizable features in the sky, a dark cloud of dust and gas silhouetted against a brighter emission nebula in the constellation Orion. It looks like the head and neck of a horse, or perhaps a chess knight, rising against a reddish background. It's a dense region where stars are forming, hidden inside the dark clouds, their light blocked by the dust until they emerge as newborn suns. The Horsehead Nebula is about 1,500 light-years away, close enough to study in detail, and it's been imaged countless times by amateur and professional astronomers alike. There's something hauntingly beautiful about it. The stark silhouette, the sense of depth and structure, the knowledge that inside that darkness creation is happening, slow and patient and inevitable. The nebula reminds us that not all darkness is empty, that some of the richest processes happen in the unseen places, that beauty can emerge from shadows as much as from light. When you think of the night sky, you probably think of stars, points of light against darkness. But the darkness itself is part of the story, full of structure and activity, and the Horsehead Nebula is a perfect example of that, a place where the darkness is the star, defining the scene as much as the light that frames it. Galaxy collisions sound violent, but they're remarkably gentle affairs. Galaxies are mostly empty space. The distances between stars are so vast that when two galaxies merge, the stars almost never actually collide with each other. Instead, they pass through one another, their paths altered by the changing gravitational fields, but direct impacts between stars are extraordinarily rare. What does happen is that the galaxies' structures are disrupted, their spiral arms torn apart and rearranged, their gas clouds compressed, triggering bursts of new star formation. Over hundreds of millions of years, the two galaxies settle into a new configuration, usually a more elliptical shape, their separate identities lost in the merger. Our own Milky Way is on a collision course with the Andromeda Galaxy, and when they meet in about 4 billion years, they'll merge into a larger galaxy, sometimes called Milkomeda. But this process will be so slow, unfolding over such immense timescales, that any civilizations present will experience it as a gradual change, not a catastrophe. The night sky will slowly shift, the stars will rearrange themselves, and eventually, Earth's descendants, if any exist, will look up and see a different sky, a blend of two galaxies worth of stars, a night more richly populated with light, a new configuration born from the slow-motion dance of two enormous structures that took billions of years to collide and billions more to settle into their new form. The International Space Station orbits Earth about 250 miles up, completing an orbit roughly every 90 minutes. If you know where and when to look, you can see it passing overhead. It appears as a bright, steady light moving smoothly across the sky, brighter than most stars, taking several minutes to cross from horizon to horizon. There are astronauts up there right now, floating in microgravity, conducting experiments, maintaining the station, looking down at Earth through cupola windows. They see 16 sunrises and sunsets every day, the Terminator line between day and night sweeping across the planet at orbital speed. They see thunderstorms flickering beneath them, the auroras glowing near the poles, city lights sparkling like scattered gems against the dark continents. They're the farthest humans from the surface of Earth, though still well within our planet's gravitational grasp, still fundamentally earthbound despite their altitude. The ISS is a collaboration between nations, a symbol of what humanity can achieve when we work together, and it's been continuously inhabited for over 2 decades now. There have been humans off the surface of Earth for that entire time, a continuous presence in space, a tiny outpost in the void. It's a beginning, a foothold, a demonstration that we can survive out there, at least in low Earth orbit, at least with constant resupply from the ground. But it's still remarkable, still worth reflecting on. Right now, as you rest, there are people above you orbiting, seeing the world from a perspective available to only a few hundred humans in all of history. Lagrange points are special locations in space where the gravitational forces of two large bodies, like Earth and the Sun or Earth and the Moon, balance with the centrifugal force felt by a smaller object, allowing that object to maintain a stable position relative to the two larger bodies. There are 5 such points for any two-body system, labeled L1 through L5. The James Webb Space Telescope orbits the Sun at the L2 point of the Earth-Sun system, about 1,000,000 miles from Earth, positioned so that Earth and Sun are always in the same direction, allowing the telescope's sunshield to block both while it observes the cold, dark universe in infrared wavelengths. Lagrange points are gravitational parking spots, useful for space telescopes and future missions. Some are stable. You could place an object there and it would tend to stay put. Others are unstable. Any drift away, and the object will continue drifting, requiring occasional corrections to maintain position. But they're real locations, defined purely by gravity and motion, invisible coordinates in space that arise naturally from the mathematics of orbital mechanics. The universe creates structure not just in matter, but in the shape of forces themselves, carving out zones and regions where physics behaves in useful, predictable ways. Gamma-ray bursts are the most energetic electromagnetic events in the universe, brief flashes of gamma rays that can release more energy in a few seconds than the Sun will emit in its entire lifetime. They're caused by the collapse of massive stars into black holes or by the collision of neutron stars, events so violent that they send beams of radiation streaming out at nearly the speed of light. If one of these beams happens to point toward Earth, we detect a gamma-ray burst, and for that brief moment the source can be the brightest object in the gamma-ray sky, despite being billions of light-years away. Fortunately, gamma-ray bursts are rare and distant, and Earth's atmosphere protects us from the radiation. The last nearby gamma-ray burst was likely hundreds of millions of years ago, possibly contributing to one of the ancient extinction events, though the evidence is debatable. The universe is capable of violence on scales we can barely comprehend, but it's also vast enough that most of that violence happens far away in other galaxies, threatening no one. The energies involved are staggering, but they're dissipated over cosmic distances, diluted by the sheer scale of space, rendered harmless by the time they reach us, arriving only as faint signals for our satellites to detect, data to analyze, mysteries to ponder. The WOW signal was a strong, narrowband radio signal detected in 1977 by the Big Ear radio telescope at Ohio State University. It lasted 72 seconds, came from the direction of the constellation Sagittarius, and was so striking that the astronomer reviewing the data wrote, "Wow," in the margin. It's never been detected again, despite repeated searches. The signal's frequency was close to the hydrogen line, a wavelength that many scientists think would be a logical choice for interstellar communication, and it had characteristics consistent with an extraterrestrial origin. But without repetition or additional data, we can't know what caused it. It might have been aliens. It might have been interference from a satellite or aircraft. It might have been a natural phenomenon we don't understand. The WOW signal remains one of the most intriguing events in the search for extraterrestrial intelligence. A tantalizing maybe, a suggestion that something out there might be trying to communicate or at least making noise loud enough for us to hear. Or it might mean nothing at all. We live in a universe full of signals and noise, and distinguishing between the two is one of our great challenges, in astronomy as in life. Planetary nebulae are shells of gas ejected by dying stars in their red giant phase, expanding outward and glowing as they're ionized by ultraviolet radiation from the hot stellar core left behind. Despite the name, they have nothing to do with planets. Early astronomers thought they looked like planetary disks through low-quality telescopes, and the name stuck. Planetary nebulae come in a stunning variety of shapes: rings, spheres, butterflies, hourglasses, irregular clouds, each shape determined by the star's rotation, magnetic fields, and whether it has a binary companion. They're beautiful, colorful, and relatively short-lived by cosmic standards, fading after a few tens of thousands of years as the gas disperses and the central star cools. The Ring Nebula in Lyra and the Helix Nebula in Aquarius are two of the most famous examples, visible through small telescopes. Planetary nebulae are what our Sun will eventually create, puffing off its outer layers in gentle pulses, leaving behind a white dwarf surrounded by an expanding shell of glowing gas. It's the Sun's final artwork, a cosmic sculpture made of its own substance, a brief but beautiful monument to a star that shone steadily for billions of years before finally releasing its outer self into the space between stars. The Goldilocks zone, or habitable zone, is the region around a star where conditions might be just right for liquid water to exist on a planet's surface. Not too hot, not too cold. Earth sits comfortably in the Sun's habitable zone, and the search for exoplanets focuses heavily on finding other worlds in their stars' habitable zones. But the habitable zone is just one factor in a planet's potential for life. You also need the right atmosphere, the right mass to hold that atmosphere, protection from radiation, a stable orbit, and probably many other factors we haven't identified yet. Still, finding exoplanets in habitable zones is exciting because it narrows the search, giving us candidates worth studying in more detail. Some stars' habitable zones are close in because the star is cool and dim. Others are far out because the star is hot and bright. Red dwarfs, the most common type of star, have habitable zones so close that planets there might be tidally locked, with one side always facing the star and the other in eternal darkness. But even those worlds might have habitable regions, bands of twilight where temperatures are moderate and life could potentially take hold. The universe is vast, and even with all the constraints, there are billions of planets in habitable zones in our galaxy alone. Somewhere out there, maybe, the conditions are right. Maybe someone else is looking up at their sky, wondering the same things we wonder, feeling the same awe and loneliness and hope. Cosmic dust is everywhere in space, tiny particles of rock and ice, some smaller than a grain of sand, others microscopic. This dust scatters and absorbs light, creating the dark lanes and regions visible in the Milky Way and other galaxies. It's also the raw material for planet formation, clumping together in protoplanetary disks around young stars, gradually building up into pebbles, then boulders, then planetesimals, and eventually planets. Every solid object in the solar system, including Earth, is made from dust that once drifted freely through space. We're dust that learned to think, collections of particles that somehow organized themselves into structures complex enough to contemplate their own origins. It's a humbling thought and also a strangely comforting one. You're not separate from the universe but continuous with it, made of the same stuff as stars and planets and nebulae, just arranged in a different pattern, a temporary configuration that happens to be conscious. The dust you came from will return to dust eventually, scattered and recycled, but right now, in this moment, it's gathered into the form of you, and that's extraordinary enough. Shooting stars, meteors, are often pieces of comet debris no larger than a pea or a grain of rice, yet they create brilliant streaks of light as they burn up in the atmosphere. The light comes not from the meteor itself burning, but from the air around it being heated to incandescence by the friction of the meteor's passage. Most meteors burn up completely, never reaching the ground. The few that do survive are called meteorites, and they're valuable to scientists because they're pieces of space that can be studied in laboratories, pristine samples of the solar system's early composition. Some meteorites are fragments of asteroids. Others come from the Moon or even Mars, blasted off those bodies by ancient impacts and eventually falling to Earth. When you hold a meteorite, you're holding something that's traveled through space for millions or billions of years, something older than any rock formed on Earth's surface, a visitor from the void. And when you see a shooting star, you're watching the end of that journey, a tiny piece of space meeting Earth in a brief, brilliant flash, a moment of light that's over almost as soon as it begins, yet beautiful and memorable enough that people stop and make wishes on them, turning cosmic debris into magic. Oort cloud comets, when they do fall inward toward the Sun, can have orbits so eccentric that they spend thousands or millions of years in the outer dark, then swing in close to the Sun for a brief visit before being flung back out into the cold. Some may even be ejected from the solar system entirely, cast out into interstellar space to wander forever. These long-period comets are unpredictable. We don't see them coming until they're already inbound, and we don't know if we'll ever see them. They're messengers from the edge of the solar system, travelers from a realm we've never visited and can barely observe, carrying ice that's been frozen since the solar system formed. When they approach the sun and begin to sublimate, they're essentially evaporating, losing mass with each pass, gradually dissipating until nothing remains but a trail of dust, and eventually not even that. Every comet is temporary, spending itself in brief displays of activity, melting away in the sun's warmth, dying slowly over multiple orbits or sometimes all at once if they venture too close and break apart. There's a melancholy to comets, a sense of doomed beauty but also a celebration. They're visible, noticed, studied, and appreciated precisely because they're ephemeral, because their time in the light is so limited and precious. Earth's rotation is gradually slowing due to tidal friction. The same forces that create ocean tides also act as a brake on the planet's spin. The effect is tiny, lengthening the day by about 1.8 milliseconds per century, but over geological time it adds up. When the dinosaurs roamed the Earth, a day was about 23 hours long. In the distant future, Earth's day will continue to lengthen, though the sun will likely die before Earth becomes tidally locked to the moon, the way the moon is locked to Earth. The lengthening of days is almost imperceptible in a human lifetime, but it's real, measurable, another reminder that even things that feel permanent and unchanging, like the length of a day, are actually in flux, evolving over deep time. Everything is process, everything is changing, just usually too slowly for us to notice directly. The universe is patient, making its adjustments over millions of years, and within that vast patience, our lives unfold in what feels like stability, but is actually a slow dance of gradual transformation. The Arctic and Antarctic circles are defined by the latitude at which the sun doesn't set for at least one day per year. The summer solstice at that latitude results in 24 hours of daylight, while the winter solstice brings 24 hours of darkness. As you move closer to the poles, the number of days of continuous daylight or darkness increases, until at the poles themselves, the sun rises once per year and sets once per year, creating 6 months of daylight and 6 months of night. Living in such conditions profoundly affects human psychology and biology, and communities in these regions have developed cultures and traditions around the extreme light cycles. But those same cycles offer opportunities: astronomical observations during the long polar night, ecological studies of ecosystems adapted to extremes. The poles remind us that Earth is not uniform, that different latitudes experience vastly different conditions, that the planet offers a range of environments and challenges, each shaping the life that inhabits it. And yet all of it is one planet, one interconnected system, variations on a theme, different expressions of the same underlying processes driven by Earth's tilt and rotation and its orbit around the sun. The observable universe has a boundary, not because the universe itself has an edge, but because light from beyond a certain distance hasn't had time to reach us yet. The universe is about 13.8 billion years old, so we can only see objects whose light has been traveling for less than that time. And because the universe is expanding, the actual distance to the edge of the observable universe is now about 46 billion light-years in any direction, making the observable universe roughly 93 billion light-years across. Beyond that boundary, the universe presumably continues, perhaps infinitely, but we can't see it and never will because the light from those regions hasn't reached us, and due to the expansion of space, may never reach us. This means we're living inside a sphere of observability, surrounded by a horizon beyond which lies the unknown. It's like being on an ocean, able to see to the horizon in all directions, knowing that more ocean lies beyond but unable to see it from where you stand. The universe might be infinite, or it might have some kind of topology we don't understand, but from our perspective it has a horizon, and everything beyond that horizon is, in a very real sense, unknowable, at least for now. We're nearing the end now, but there's no rush. Let the facts continue to flow over you like water, like the gentlest tide. You don't need to hold on to them. They're just here to keep you company, to fill the space between wakefulness and sleep with something soft and curious and kind. Your breathing is steady. Your body is heavy and relaxed. The universe turns, the stars shine, and you can simply rest within it all, a small consciousness cradled by vast forces, held safely in this moment. Black holes can have different sizes. Stellar mass black holes formed from collapsed stars might have a few times the sun's mass. Supermassive black holes lurking in the centers of galaxies can have millions or billions of solar masses. Our own galaxy has a supermassive black hole at its center, called Sagittarius A*, with a mass about 4 million times that of the Sun. It's about 26,000 light-years away, safely distant, and it's relatively quiet, not actively consuming much material at the moment, just sitting there, a gravitational anchor around which the galaxy rotates. Occasionally, a star or gas cloud wanders too close and gets shredded by tidal forces, creating a brief flare of radiation as the material heats up while falling in. But mostly our galactic black hole is dormant, a dark heart that holds the galaxy together without fanfare. In some galaxies, the central black holes are actively feeding, pulling in enormous amounts of matter and creating brilliant quasars, galaxies so bright they outshine all their stars combined. But our black hole is quieter, more restrained, and that's probably fortunate for us. We wouldn't want to live too close to an active galactic nucleus, with its jets of radiation and energetic particles. Our galaxy is calmer, more peaceful, a place where stars and planets can form and evolve without excessive disruption, and the black hole at the center, for all its gravitational power, is part of that peace, a stabilizing presence rather than a threat. The concept of now is complicated in astronomy because of light's travel time. When you see the sun, you're seeing it as it was 8 minutes ago. When you see a star 100 light-years away, you're seeing it as it was 100 years ago. So what does now mean on cosmic scales? If you could somehow freeze time across the entire universe at this instant, what would you see? Every object as it currently is, not as it was when its light left. But you can never actually see that. You're forever trapped in the past, seeing everything as it was, not as it is. And because of relativity, now isn't even universal. Different observers in relative motion have different definitions of which events are simultaneous. The universe doesn't have a single universal now. Time is flexible, relative, tangled up with space and motion. This can feel disorienting, but it also means that the past is always with us, literally visible in the light from distant objects, accessible for study and contemplation. The sky is a record, a living archive of history written in light, and we're constantly receiving transmissions from the past, messages sent long ago that we're only now reading. Asteroids are rocky remnants from the early solar system, most of them orbiting in the asteroid belt between Mars and Jupiter. They range from tiny boulders to objects hundreds of miles across, like Ceres, which is large enough to be classified as a dwarf planet. Asteroids are leftovers, pieces that never assembled into a planet, prevented from doing so by Jupiter's strong gravity, which stirred them up and kept them from clumping together. They're valuable scientifically because they're largely unchanged since the solar system's formation, time capsules preserving the conditions of that era. Some asteroids are made of metal, iron, and nickel, possibly the cores of small bodies that were shattered by collisions. Others are rocky, and some contain water, ice, and organic molecules. There's even been serious discussion of mining asteroids in the future, extracting metals and resources that are rare on Earth but abundant in some asteroids. But for now, they're mostly studied from afar, occasionally visited by spacecraft, sometimes impacting Earth in events that range from harmless shooting stars to civilization-threatening catastrophes, though the latter are extremely rare. The asteroid belt sounds dangerous, but it's mostly empty space. The asteroids are spread out over such a vast volume that you could pass through the belt without coming anywhere near one. Space is big, and even the asteroid belt, crowded by cosmic standards, is still mostly void. Space telescopes have revolutionized astronomy by observing wavelengths of light that don't penetrate Earth's atmosphere. The Hubble Space Telescope observes in visible, ultraviolet, and near-infrared. The James Webb Space Telescope specializes in infrared, seeing through dust clouds and looking at very distant, very redshifted galaxies. Other telescopes observe in X-rays, gamma rays, radio waves, each wavelength revealing different phenomena. Hot gas around black holes glows in X-rays. The cosmic microwave background radiation is visible in microwave wavelengths. Pulsars emit radio waves. By observing the universe across the entire electromagnetic spectrum, we build up a complete picture, seeing the universe not just as it appears to human eyes, but in all the ways it radiates energy. Some objects that are invisible in visible light blaze brightly in other wavelengths. Some structures only become apparent when viewed in infrared or radio. The universe is richer and more complex than any single wavelength can reveal, and our multi-wavelength approach to astronomy reflects that, building instruments to see what our eyes cannot, extending our senses across the full range of light and beyond, into gravitational waves and neutrinos, capturing every possible signal the cosmos sends our way. The oldest light in the universe is the cosmic microwave background radiation, the afterglow of the Big Bang, released when the universe was about 380,000 years old. Before that, the universe was so hot and dense that matter and radiation were constantly interacting, making the universe opaque, like a thick fog. But as the universe expanded and cooled, electrons and protons combined to form neutral hydrogen, and light could suddenly travel freely. That light has been traveling ever since, redshifted by the expansion of space from visible wavelengths into microwaves, filling the entire universe with a faint glow at a temperature of about 2.7 Kelvin. The CMB is remarkably uniform, almost the same temperature in every direction. But there are tiny fluctuations, regions that were slightly denser or less dense, and those fluctuations are the seeds of all the structure we see today. Galaxies, galaxy clusters, the cosmic web. The CMB is a baby picture of the universe, showing us what it looked like in its infancy, and studying it tells us about the conditions then and the processes that led to now. It's the oldest thing we can see, a whisper from the beginning, still audible if you know how to listen. Orbital resonances occur when two orbiting bodies exert regular, periodic gravitational influences on each other, because their orbital periods are related by a ratio of small integers. Pluto and Neptune are in a 3-2 resonance. For every 2 orbits Neptune makes, Pluto makes 3, and this relationship keeps them from ever colliding despite Pluto's orbit sometimes being closer to the Sun than Neptune's. Jupiter's moons show multiple resonances. Io, Europa, and Ganymede are locked in a 1-2-4 resonance, their orbits synchronized in a way that keeps them stable and also pumps tidal energy into Io, making it the most volcanically active body in the solar system. Resonances can stabilize orbits or destabilize them, clearing out regions of space or concentrating objects in specific zones. The Kirkwood gaps in the asteroid belt are regions where resonances with Jupiter have cleared out asteroids, creating empty bands in an otherwise populated belt. The universe loves patterns, loves ratios and relationships, and orbital resonances are one expression of that, gravity creating order, synchronizing motion, turning chaos into rhythm. The heliosphere is a bubble of charged particles blown out by the solar wind, extending far beyond the planets, protecting the inner solar system from much of the interstellar radiation and cosmic rays. The Voyager spacecraft crossed the heliopause, the boundary of the heliosphere, and entered interstellar space, sending back data from beyond the Sun's direct influence for the first time. The heliosphere isn't a perfect sphere. It's shaped by the Sun's motion through the galaxy, stretched out behind like a comet's tail, and its exact shape and size fluctuate with the solar cycle. Inside this bubble, we're somewhat shielded from the harsher environment of interstellar space. The heliosphere is our Sun's domain, the region where its influence dominates, and it's much larger than the solar system as we usually think of it. The planets are tucked in close to the Sun. The heliosphere extends far beyond, tens of billions of miles, wrapping the solar system in a protective envelope that we don't often think about but which plays a crucial role in making our corner of space a bit more hospitable to life. Titan, Saturn's largest moon, is the only moon in the solar system with a thick atmosphere, and it's a strange, fascinating world. The atmosphere is mostly nitrogen like Earth's, but it's laced with methane, and the surface is cold enough that methane exists as a liquid, forming lakes and rivers, the only other body in the solar system known to have stable liquid on its surface. But it's liquid methane and ethane, not water. The temperature is about -290 degrees Fahrenheit, far too cold for water to be liquid, but just right for methane. Titan has weather, methane rain, methane clouds, possibly methane snow. It has seasons, dunes, mountains, and a subsurface ocean of liquid water far below the icy crust. It's like a bizarre, frozen version of Earth, with similar processes playing out in different materials. Studying Titan gives us insight into how worlds work, how atmospheres and surfaces interact, how climate systems develop. It's also been suggested as a possible abode for life. Though any life there would be radically different from Earth life, perhaps using liquid methane as a solvent instead of water. Titan is a world of possibilities, strange and cold but dynamic and complex, one of the most intriguing objects in the solar system. The Milky Way is on a collision course with several smaller galaxies that are currently being absorbed, their stars and gas stripped away and added to our galaxy. The Sagittarius Dwarf Elliptical Galaxy is one example, a small galaxy that's been looping around the Milky Way and is slowly being torn apart by tidal forces, its stars scattered into long streams that wrap around our galaxy. This process has been going on for billions of years, and it will continue. Galaxies grow by consuming smaller galaxies, and the Milky Way has grown this way, and it will continue to grow until it eventually merges with Andromeda, creating a new, larger galaxy. It's a violent process in the sense that structures are destroyed, but it's also a creative process. Mergers trigger star formation, redistribute gas, and build larger systems. And from the perspective of any individual star, it's gentle. The star just continues its orbit, perhaps around a new center but otherwise unaffected. Galactic dynamics play out over scales so large that the violence is softened, spread out, rendered almost peaceful by the sheer size and timescale involved. The Chandrasekhar limit is the maximum mass a white dwarf can have, about 1.4 times the Sun's mass. If a white dwarf exceeds this limit, electron degeneracy pressure can no longer support it, and it collapses, triggering a Type Ia supernova. This limit is important because Type Ia supernovae are so consistent in brightness that they're used as standard candles to measure cosmic distances. The consistency comes from the fact that they all result from white dwarfs crossing the same mass threshold, so they all explode with roughly the same energy. This discovery led to the realization that the universe's expansion is accelerating, a finding that earned a Nobel Prize and introduced the concept of dark energy. Limits and boundaries in physics often mark phase transitions, points where the rules change and new phenomena emerge. The Chandrasekhar limit is one such boundary, a threshold encoded in the laws of physics, a number that determines the fate of stars, and indirectly has told us profound things about the universe's future. The Fermi paradox asks, if the universe is so vast and there are so many stars and planets, where is everybody? Why haven't we detected any signs of alien civilizations? Maybe life is incredibly rare. Maybe intelligence is rare. Maybe civilizations tend to destroy themselves or go quiet. Maybe they're out there but we're not looking in the right way or haven't been looking long enough. Maybe they're deliberately avoiding us, or maybe the universe is full of life but it's just too far apart for communication. The distance is too vast, the timescale's too long. The Fermi paradox is less a paradox and more a question, one that highlights how little we know about life's prevalence and the likelihood of intelligence and technological civilizations. It's possible we're alone, or at least alone in our galaxy or in this era. It's also possible we're not, and we just haven't found each other yet. Either answer is profound. If we're alone, we're extraordinarily special, the universe's one experiment in consciousness, at least in our corner of space. If we're not alone, then the universe is filled with perspectives and experiences and stories we can't yet imagine. Both possibilities inspire awe, and neither diminishes the wonder of existence. Enceladus, a small moon of Saturn, has geysers erupting from its south pole, spraying water, ice, and organic molecules into space. These geysers come from a subsurface ocean beneath the icy crust, kept liquid by tidal heating as Saturn's gravity flexes and squeezes the moon. The Cassini spacecraft flew through the plumes, sampling the material, and found not just water but complex organic molecules, salts, and other ingredients that could, potentially, support life. Enceladus is now considered one of the most promising places to search for life in the solar system, and future missions are being planned to return and study it in more detail. It's a tiny moon, only about 300 miles across, but it has an ocean, warmth, organic chemistry, and energy, everything we think life needs. If life exists there, it would be hidden beneath miles of ice, living in a dark ocean heated by tidal forces, completely independent of the sun. It would prove that life can arise in environments very different from Earth, expanding the range of habitable worlds, and suggesting that the universe might be more alive than we currently imagine. Solar cycles are roughly 11-year periods during which the sun's activity waxes and wanes. At solar maximum, the sun has more sunspots, more solar flares, more coronal mass ejections, bursts of energetic particles that can affect Earth's magnetic field, creating auroras and occasionally disrupting satellites and power grids. At solar minimum, the sun is quieter, with fewer sunspots and less activity. These cycles are driven by the sun's magnetic field, which flips polarity roughly every 11 years, though the exact mechanisms aren't fully understood. The cycles are remarkably regular but not perfectly so. Some maxima are stronger than others, and the timing can vary. We are currently in solar cycle 25, which began around 2020. The sun's activity affects space weather, which in turn affects Earth, so understanding and predicting solar cycles is important for protecting our technology and infrastructure. But from a human perspective, the cycles are mostly invisible. We don't feel them directly, just occasionally see more vivid auroras or hear about satellite disruptions. The sun is dynamic, changing, but its changes are gentle enough that life on Earth continues unaffected, shielded by our atmosphere and magnetic field. Quasars are among the most luminous objects in the universe, powered by supermassive black holes actively consuming enormous amounts of matter. The infalling material forms an accretion disk that heats up to millions of degrees, emitting vast amounts of light and other radiation, sometimes outshining the entire galaxy that hosts the black hole. Quasars are mostly found in the distant universe, meaning we're seeing them as they were billions of years ago, when galaxies were younger and more actively forming stars, and central black holes were more actively feeding. In the local, modern universe, most black holes are quieter, their host galaxies having settled down. Our own galactic black hole could become a quasar if enough material fell into it, but that's unlikely. There's not enough gas and dust in the vicinity to fuel such activity. Quasars are windows into the early universe, showing us what young galaxies looked like, how they evolved, how black holes and galaxies influenced each other in the cosmic past. They're also so bright that they can be used as backlights, their light passing through intervening gas clouds, allowing us to study the composition and structure of the intergalactic medium by observing what wavelengths are absorbed. The moon illusion is a psychological effect where the moon appears larger when it's near the horizon than when it's high in the sky, even though its angular size is essentially the same. The illusion has been known for thousands of years, and there are various explanations. Our brains compare the horizon moon to nearby objects like trees and buildings, making it seem larger, or the flattened appearance of the sky dome tricks our perception. Whatever the cause, it's a reminder that perception isn't a perfect representation of reality, that our brains interpret sensory input in ways that can mislead us. The moon doesn't change size as it rises, but it feels like it does, and that subjective experience is real even if the objective measurement contradicts it. We navigate the world through perception, through the stories our brains tell us about what our senses are detecting, and those stories are usually useful but not always accurate. The moon illusion is harmless, even pleasant. It makes the rising moon feel more dramatic, more impressive, and there's no reason not to enjoy that, even knowing it's an illusion. Beauty and wonder don't require objective accuracy. They just require the experience, and the experience is real enough. Space isn't completely empty. It's filled with the interstellar medium, a thin soup of gas and dust, about 1 atom per cubic centimeter on average. That's incredibly sparse by Earth standards. Our atmosphere has about 10-19 atoms per cubic centimeter. But space is so vast that even this thin medium contains an enormous amount of mass overall. The interstellar medium is the raw material from which new stars form, and it's enriched by the deaths of old stars, creating a cycle of matter through stellar life cycles. Some regions are denser, forming nebulae where stars are born. Others are nearly empty voids. The medium also contains cosmic rays, magnetic fields, and radiation, making it a complex environment despite its emptiness. When spacecraft travel through interstellar space, like Voyager has, they detect this medium, measuring its density and composition, sending back data about the space between stars. It's not the absolute void we once imagined, but a subtle, structured environment, varying in density and temperature, shaped by stellar winds and supernova explosions, threaded with magnetic fields, slowly mixing and evolving, a dynamic component of the galaxy's ecology. The Great Rift is a series of overlapping dust clouds in the Milky Way that creates a dark lane running through the bright band of the galaxy as seen from Earth. In dark skies, it's quite noticeable. The Milky Way appears split by this dark river running through it. Ancient cultures noticed the rift and incorporated it into their mythology. The Inca, for example, saw the dark areas of the Milky Way as constellations, shapes formed by the absence of light rather than the presence of stars, a concept called dark constellations. They saw animals, a llama, a fox, a toad, outlined in darkness. It's a different way of seeing the sky, focusing on the shadows rather than the lights, finding meaning in what's not there as much as in what is. The Great Rift is simply dust blocking the light of more distant stars, but it's a reminder that darkness can have structure and significance, that absence can be as meaningful as presence, that the negative space in any composition can shape the whole as much as the positive space. The habitable zone is sometimes called the Goldilocks zone, but habitability is about more than just temperature. You need a stable star, a planet with the right mass to hold an atmosphere but not so much that it becomes a gas giant, protection from radiation, a magnetic field to shield against solar wind, stable orbit and rotation, water or some other solvent, and probably many other factors. Earth has all of these, which is why we're here, but how common is that combination? We're starting to find rocky planets in habitable zones, but we can't yet determine if they have atmospheres, oceans, magnetic fields, or life. The next generation of telescopes will begin to answer these questions, analyzing exoplanet atmospheres for biosignatures like oxygen and methane in combinations that suggest biological activity. It's a slow process, but we're getting there, developing the tools and techniques to not just find planets, but to study them in detail, to determine which might be truly habitable and which might actually be inhabited. The search for life beyond Earth is one of the great scientific endeavors of our time, and it's moving from speculation to observation, from philosophy to data. And the answers, whatever they turn out to be, will fundamentally change how we see ourselves and our place in the cosmos. And so we reach the end of this gentle journey through the night sky, though really there is no end. The sky continues, always turning above us, filled with more wonders than we could ever catalog, more stories than we could ever tell. You've been such a wonderful companion on this exploration, whether you're still awake, hovering at the edges of consciousness, or already deeply asleep, these words becoming part of your dreams. The night sky has been humanity's constant companion for as long as we've existed. Our ancestors looked up at the same stars, though they had different names for them, different stories to explain their patterns. They navigated by those stars, marked time by them, found meaning in their movements. And now, thousands of years later, we look up with different tools and different knowledge, but the same sense of wonder. We've learned that those points of light are suns like ours, some smaller and cooler, others larger and hotter, all burning in the darkness, all separated by distances so vast that light itself takes years to bridge the gaps between them. We've learned that some of those stars have planets, and that some of those planets might be like Earth, and that maybe, just maybe, someone on one of those worlds is looking back in our direction, seeing our sun as just another faint star in their alien sky, wondering if they're alone. The universe is vast beyond comprehension, yet here you are, tucked safely into bed, on a planet that orbits an ordinary star in an ordinary galaxy, and somehow that ordinariness is part of what makes it all so beautiful. We're not at the center of anything. We're not special in any cosmic sense. We're just here, part of the vast tapestry, one thread among countless others. And yet we're the thread that's aware, that can look out at the rest of the tapestry and appreciate it, that can feel awe and wonder and curiosity. That counts for something. That counts for a lot. Tonight, as you drift toward sleep, you can carry with you the knowledge that the sky is always there, always turning, always filled with light and darkness in equal measure. The stars are shining right now, even if you can't see them, even if clouds cover them or city lights wash them out. They're there, patient and eternal, and they'll be there tomorrow night and every night after. The cosmos doesn't demand anything from you. It doesn't need your understanding or your attention or your wonder, though it accepts all of these gracefully when offered. It simply exists, vast and old and full of mysteries that will take generations to unravel, if we ever unravel them at all. Thank you for spending this time with me, for letting these words and ideas wash over you, for being open to the gentle strangeness and beauty of the universe we inhabit. If you enjoyed this journey, I'd be grateful if you'd subscribe to the channel, leave a like, maybe leave a comment sharing what your favorite fact was or what helped you relax. But if you're already asleep, that's even better. That's the whole point, really, to help you find that soft place where thoughts dissolve and rest begins. Sleep well, dear listener. Let the night sky watch over you as it has watched over countless others before you. Let the stars shine in their distant silence. Let the darkness be gentle and the dreams that find you be peaceful. You're part of something vast and ancient and ongoing, and right now, your part in that vastness is simply to rest, to let go, to breathe slowly and deeply, and to trust that the universe will keep turning without your vigilance, that you can set down the day's burdens and simply be, held safely on this small blue world that orbits a patient star in a spiral arm of an ordinary galaxy, surrounded by wonders you don't need to understand to be cradled by. Good night. Sweet dreams. And may the cosmos, in its infinite patience and its ancient rhythms, carry you gently into the deepest, most restful sleep.